So in this example, we have a bar magnet just staying still right here, and we've got a loop of wire that we are moving to the right. And we want to know, does this motion result in any induced current? And if so, in which direction? So for induced current to happen, we've got to have induced voltage. Usually written as epsilon induced. And what has to be happening in order to cause induced voltage in the first place?
The magnetic flux has to change.
Yeah, there's got to be some sort of change in the magnetic flux. And usually we would write that as the derivative of flux with respect to time. This signifies that the flux has to be changing as time passes in order for there to be induced voltage. And the faster the flux is changing, the more voltage you get. We also generally write this with a negative sign, just signifying that the induced effect is in a direction opposite to the change. So whatever direction the flux is changing in, the induced voltage is in a direction opposite to that, using the right-hand rule. But of course, first thing we need to check is the flux changing at all? And to do that, we're going to need to draw the magnetic field in this region. Because we're defining flux as area times magnetic field times cosine of the angle between the magnetic field and the normal vector. By the way, this is the same as how we technically define flux for Gauss's law, using the electric field instead of magnetic field usually for Gauss's law. It's just that for Gauss's law, we're talking about some sort of enclosed surface wrapping around some region of space. In this case, though, we're just talking about the surface within that loop of wire. So it's not really a surface that encloses some region. But it's still the same sort of quantity. We're just talking about a different type of surface. So we've got this region inside the wire loop, the surface inside the wire loop, and we want to know the magnetic field caused by this bar magnet. And what does the magnetic field from a bar magnet look like? How should we draw out these field lines? Yeah, from north, we're coming out of the north end and looping around to the south end. So we're going to have field lines. A field line coming straight out of the north end is just going to keep going straight. One going straight into the south end just keeps going straight. But anything coming out of the north end in an angle is going to loop around to the south end. Something like that. Of course, within the magnet itself, you get different looking effects. The field lines don't just stop at the south end. The field lines keep going through the magnet, which you can see by, for instance, cutting a hole in the magnet and putting a compass in the hole. You'll find that the compass still orients in this direction. So these field lines actually form loops. They don't just start or stop anywhere. And notice that they're bunched very close together inside the magnet. This is because if you put a magnet there or a compass there, it'll twitch very rapidly to align with the existing magnetic field, suggesting a very strong magnetic field. So we're going to have loops kind of like this, but all we really care about is the magnetic field in the vicinity of the loop of wire itself. Magnetic field in that region is pointing to the left. Any questions on the shape of that magnetic field so far? And we also need to choose a normal vector because we have an area, we have a magnetic field, we need a normal vector so we can establish an angle. For the normal vector, if we've got this loop of wire, what would be our options for a vector perpendicular to this loop?
Into or out of a page?
Yeah, if we've got a wire oriented this way, our options for normal are inwards or outwards. And we could choose either one here. Usually you'd want to choose the one that most closely agrees with the existing magnetic field. But if our options are inwards or outwards, Either way, what's the angle that this vector makes with the magnetic field vector?
90 degrees?
Yeah, those vectors, the outwards normal vector and the leftwards magnetic field vector, those are at a 90-degree angle. So theta here is 90 degrees. And in this case, that's true no matter which normal vector you choose, outwards or inwards. So we get area of the loop times magnetic field in that region times cosine of 90 degrees. And what's cosine of 90 degrees?
0.
Right. A times B times 0 is 0. So this is a zero flux situation. Now, having no flux doesn't mean there's no induced current, though, because induced current or induced voltage is not about the amount of flux, it's about how quickly the flux is changing. But if all we're doing here is taking this loop of wire and dragging it to the right, as we move it to the right, now how much flux does it have?
Wouldn't it still be 0 because the magnetic field is still going left?
Exactly. We've still got the same directions involved. We are moving it to a location of weaker magnetic field. So area is the same, B is smaller, but cosine of 90 is still 0. So even though we've moved it to a region of weaker magnetic field, we haven't actually changed the flux because the magnetic field is still perpendicular to the normal vector. So if the flux starts at 0 and ends at 0, then there's no change in flux. The flux is just this constant value of 0. No change in flux means no induced voltage, which means no current will flow. So in this situation, we get no current at all. Any questions on that so far?
Casey, I just have a really quick side question. Will the induced current always be like clockwise or counterclockwise, or can it be like down, up, left, or right as well?
Well, we're talking about a loop of wire. So the current is going to flow around the loop. And so if you're looking at that loop from a particular perspective, you can say from this perspective, the current is flowing clockwise, or from this perspective, the current is flowing counterclockwise.
Oh, okay. Okay, thank you.
So let's try a different example where we might actually get some current. In fact, let's talk about the same wire loop, still moving to the right, but let's create a magnetic field with something different. Let's create a magnetic field using wire with current. Let's say we have a long wire with current already flowing through it, a powered wire. Presumably this wire is hooked up to a battery or a generator or something. And it already has current, so current flowing, let's say current flowing upwards. So this is the source current that's creating a magnetic field. And which direction would you say the magnetic field is that's caused by this current? How could we figure out the direction of the magnetic field that it creates? Yeah, first right-hand rule. And since we want to care about the magnetic field around this wire, probably the most convenient way to do this would be to point your thumb in the direction of the current and wrap your fingers around in the direction of the magnetic field. So current, magnetic field, we're going to get magnetic field going out on the left side, wrapping around to the right in front of it, wrapping around to inwards, so inwards on the right side, and then wrapping around to the left behind the wire. So something like this. So to the right in front of it, wrapping around to the left behind it. But most importantly, on the right side, it's going to be going inwards. On the left side, going outwards. So that's the direction the magnetic field is pointing all around this powered wire. All we care about, though, is the magnetic field in the vicinity of this wire loop. The wire loop is on the right side of the powered wire, so that's an inwards magnetic field. which means what should we choose as the normal vector?
As well.
Yeah, we have the options of outwards or inwards because that's perpendicular to the surface. We want to choose the one that most closely aligns with the existing magnetic field to make things more easy to visualize. So we'll choose a normal vector pointing into the board. At this point, what's our new angle? Between the normal vector and the magnetic field vector. Yeah, we've got a 0 degree. Anytime you've got two vectors pointing in the same direction, the angle between them is 0. There's no difference in their direction. So if we plug in 0 for theta, cosine of 0 is 1. So we just get A times B. So this actually does have some flux. In fact, it's got quite a lot of flux. So this is experiencing magnetic flux. There are magnetic field lines going through the interior of the loop. And the amount is area times the strength of the magnetic field. The big question though is not, is there a flux, but does the flux change? As we take this loop of wire and move it to the right, is any of this going to change?
Will it change because the strength of the magnetic field will decrease?
Yeah, if we move further away from the source wire, we should expect a decreasing magnetic field. We're going to have a very strong magnetic field close to the source, then getting weaker and weaker and weaker and weaker. So the magnetic field gets weaker and weaker the further you get from the source. The area is staying the same, but the magnetic field is getting weaker, so the flux overall is diminishing. We're getting a decreasing amount of flux. So the flux decreases because the magnetic field is getting weaker and weaker the further out we go. So there is a change in flux, which means we do get induced voltage. This loop of wire is going to have current as if there were a tiny invisible battery in it somewhere. And of course, there is no actual battery, no physical battery. It's just that the changing magnetic situation creates extra voltage. Does it matter if the velocity is constant? Not in terms of whether or not there is voltage. I mean, just the fact that this is moving to a region with different magnetic field means the flux is changing, which means you get an induced voltage. The rate at which you're moving it is going to influence how much voltage you get. For instance, if you're moving it very quickly, the flux is changing very quickly, so you get a lot of voltage. If you're moving it very slowly, the flux is changing slowly, so you only get a little bit of voltage and therefore only a little bit of current. Of course, that would be a little bit of current for a longer period of time. So the overall effect might be the same in the long term. But the rate of the amount of voltage you get depends only on how fast the flux is actually changing. Any other questions on that so far? So knowing the amount of voltage is going to depend on how fast AB is changing. So presumably we could, if we knew the velocity, and we could even use the formula for magnetic field. We could say magnetic field equals mu naught times I over 2 pi r. Mu naught, I, and 2 pi are all constants. If you take the derivative of this though, because we'd have area times magnetic field, if we were going to take the derivative of that, we could actually figure out how much voltage. Derivative of area times all this. Area times mu naught times I over 2 pi r. What's the only part of this that's actually changing as time passes?
R is changing?
Yeah, the radius is changing. A is the area of the loop. We're not changing the size of the loop. That's a rigid loop. Current in the original wire, the source wire, is not changing. Mu naught and 2 pi are universal constants, of course. But R is the distance from the source wire to the location of interest. If we are moving the loop further and further from the source, we are actually increasing R. So R is changing, everything else stays the same. That means we can pull all these constants out of the derivative. I'm going to ignore the negative for the moment, just look at how much it is, the magnitude. If we pull out those constants, area times mu naught divided by 2 pi, and also times current, then all that's left is derivative of 1 over R. Anyone remember the derivative of 1 over R?
Is it negative 1 over R squared?
Yeah, that should work. This R to the negative 1 becomes, you just diminish the exponent by 1 and also multiply by the original exponent. So we get 1 over R squared with a negative. Again, I'm going to ignore the negative because we don't really care about direction yet. So we get A times that universal constant times current divided by 2 pi times 1 over R squared. But because of the chain rule, we also need to multiply by the derivative of what's inside, the derivative of R itself. And what is the derivative of position? The derivative of distance? What do we call how much the position changes divided by how much time passes?
The velocity?
Exactly. This is the velocity. Derivative of position is velocity. So that means the induced voltage that you get in this loop of wire is dependent on area of the loop, current in the source wire, velocity, and also how far you are. So you can actually use this to calculate how much voltage you get as a result of this motion. So the faster you're moving this loop, the more voltage you get. The stronger the current in the original wire is, the more voltage you get. The larger this loop of wire is, the more voltage you get. The further you are from the source wire, the less voltage you get. So we can get all those proportionalities using this formula. So we can use something like that to figure out how strong the voltage is. And then you can also figure out how fast current is going to flow. Think back to what we were looking at in terms of circuitry in Physics 7b. What's the relationship between voltage and how fast the current is flowing? It might help to think of this loop of wire as having a little bit of resistance. What's the usual formula for delta V for a resistor?
Negative IR.
Right. And again, I'm going to ignore the negative for the moment and just look at the amount. So the voltage that we get from the induced effects should equal current times resistance. Divide both sides by resistance, and we find the induced current in the loop is proportional to the current in the original wire, but also proportional to all these other things as well. The area of the loop, the resistance of that loop of wire, the distance from the original wire, and the speed at which this loop is being moved. So those all are going to matter in terms of establishing how much current you get in this loop of wire. But the overall result, let's say this is like a light bulb or something, you take this loop of wire and move it, and you cause that light bulb to light up. This light bulb is going to glow because of the motion you created. By doing work to it, your mechanical energy is turning into light because of the electrical circuit. So that's really one of the main uses of this. This sort of arrangement, I mean, not exactly this arrangement. You don't have people grabbing a loop of wire and pulling it. But usually arrangements involving some sort of spinning loop of wire in the presence of a strong magnetic field can be used to turn mechanical energy into electrical energy. So this is the basics of how most power generators work. You use some sort of source of energy. Maybe you're burning wood, or maybe you're hooking up a turbine and letting the wind turn it, or maybe a water wheel on a dam. Any sort of source of mechanical energy that can do work to make some loop of wire spin. That spinning loop of wire in the magnetic field converts the mechanical energy into electrical current, electrical energy. And this is how most power plants create electrical current. Some exceptions are solar cells use more of a quantum effect in order to convert the light into motion of electrons. And geothermal usually just uses the geothermal to boil water and uses the boiling water to turn some turbine. But most power plants are just some way of using work to make a turbine spin, and then using that to spin a loop of wire in the presence of a magnetic field to create induced voltage. Any other questions on that so far? Another induced current example? Yeah, but first of all, let's finish this one up, because the one thing we haven't done is the velocity. We figured out a formula for how much current, but we still want to know which direction is the current flowing. Is it flowing clockwise in this loop, or is it flowing counterclockwise in this loop? So to figure that out, we can use the negative sign here. Going back to Faraday's law, Faraday's law tells us how much voltage to expect. The negative sign, though, is telling us the direction. And sometimes this negative sign, the information about the direction, is called Lenz's law. Lenz's law tells us the direction. Faraday's law tells us the amount of voltage. And Lenz's law is basically just saying this negative sign means that the direction of the final result, the direction of the current flowing, is opposite to the direction of the change in flux. So let's establish some directions here. We know the flux is in the process of decreasing. If we're moving this to the right, the flux is decreasing because we're moving to a weaker magnetic field. We want to interpret that as a direction, though. And even though flux is technically a scalar and not a vector, it technically does not have a direction. We can generally interpret flux as being in the direction of the normal vector we chose. So we chose an inwards normal vector so as to match up with the existing magnetic field. But flux is getting weaker. We got an inwards vector that's getting weaker and weaker and weaker and weaker. If you got an inwards vector that's getting weaker, that's a change in which direction? There's nothing moving up or down here. And we're not looking at it in terms of positive and negative. We're looking at it in terms of directionality. If you treat flux as inwards, but it's getting weaker, which direction is the change?
It's outward.
Yeah, should be in the outwards direction. Inwards, but getting weaker is a change in the outwards direction. Like if it were inwards and getting stronger, that would be a change in the inwards direction. But inwards and getting weaker is a change in the outwards direction. Just like upwards but getting weaker is a change in the downwards direction. Or for instance, to the north and getting weaker is a change in the southwards direction. But in this case, we've got an inwards vector, if we treat flux as a vector temporarily, that's getting weaker. So that's a change in the outwards direction. So the d flux dt can be treated as an outwards change, but the negative sign says take the opposite of that direction. So an outwards change in flux reversed tells us the induced effect. We should expect an induced effect curling this way. So outwards change reversed, use the right-hand rule. We should expect current circulating this way. So that's going to be clockwise. So we expect current to flow clockwise in the loop of wire. And then as one final check, you can look at the magnetic field that that induced current creates, because any current flowing in a loop creates its own magnetic field. So this induced current creates magnetic field inwards, and that inwards magnetic field is opposite to the decrease in flux. Yeah, if we have, so going back to the idea of Faraday's law saying that the induced effect is opposite to the change in flux, the flux is pointing inwards because we're treating the normal vector as inwards. Flux can be treated as being in the direction of the normal vector. Inwards flux, but getting weaker. So an inwards vector that gets weaker and weaker is a change in the outwards direction. Outwards change, but the negative sign in Faraday's law says reverse that. And that right-hand rule tells you the direction of the induced current. So inwards flux getting weaker is an outwards change. Outwards change, reversed because of the negative sign, becomes clockwise current. And the direction of the curl of the fingers. Yeah, from your perspective, clockwise current. And if it's drawn like this, I think you don't really need to specify a perspective. It's just from your perspective, from the viewer's perspective by default. But if you've got like a loop of wire that's on its side like this, if you got current circulating like this, you want to say like clockwise when viewed from the left or clockwise when viewed from the right.
I have a question.
Mm-hmm.
So basically, so can you explain the epsilon? Like, what does it like mean again?
Oh, this epsilon is voltage, the induced voltage. This is the same epsilon we were using for batteries back in 7B. Like epsilon for a battery is just the amount of voltage boost, the delta V voltage boost that a battery provides. This is the same idea. This is a voltage boost, but in this case, it's not caused by a battery, it's caused by the changing flux.
Okay, and then are we like, so basically the, why we're changing it, like, is it a negative charge?
No, it's just that the resulting effect is in a direction sort of pushing back against the change. It's very similar in that there's a lot of situations where you make some change and you get a result that pushes back against that change. Like springs, for instance. If you take a spring and push it in one direction, the spring exerts a pushback in the other direction. If you've got an object that's moving in a region with some friction, you've got motion in one direction and the force of friction pushing back in the other direction. This is a very similar sort of pushback. If you make some change to the situation, in this case, moving it to a weaker magnetic field, you get a result, in this case, induced current flowing, creating an effect that pushes back against that. Like conceptually, we're moving this to a weaker magnetic field. That is an inwards magnetic field that's getting weaker and weaker and weaker. But the induced current is creating its own magnetic field in the inwards direction, partially counteracting the inwards magnetic field getting weaker. So the final induced effect is in a direction opposite to the change that caused it in the first place. It's not like it cancels it out. The extra magnetic field caused by the induced current doesn't cancel out the existing magnetic field. It just acts in a direction opposite to the change.
Okay, so so after like, so usually for like these type of questions, like they ask like, oh, how do we want the current to be flowing, in order to like get the like I mean, like in which direction will the induced current be?
Yeah.
So
what you want to figure out is how fast or which direction. First of all, is there going to be any induced current? Is the flux changing? And then if there is current, which direction will it flow? And maybe even how fast is the current going to flow? How strong is the current?
So would that be the V then?
V tells you how much voltage you get, but Ohm's law is that for any resistor, and we can treat the wire in the loop as a resistor. It's just going to have very small resistance. Delta V is negative I times R. Or if you're looking at it as absolute value, just I times R. So if you have the delta voltage, that is the current or the voltage induced by the changing flux, you can divide by resistance of the loop to figure out how fast the current is going to flow. Any other questions on that?
Yeah, so basically the direction that the current is gonna flow, is that the same thing as like that what you were talking about before, where it's like it's gonna push back or something? Is that the same thing?
Well, the current in this case is flowing clockwise, but that current creates its own magnetic field in the inwards direction based on right-hand rule. Curl your fingers in the direction current's flowing, and your thumb tells you the direction of the magnetic field inside the loop. That final induced magnetic field is in the inwards direction, which acts opposite to the existing magnetic field getting weaker. Because we've got an inwards magnetic field from the original source. We're moving to a location with a weaker and weaker and weaker magnetic field. So the induced current creates a magnetic field in that direction to partially balance that out or to oppose the change.
Okay, yeah, that makes sense. Thank you.
Mm-hmm. And part of the reason why we get this opposing the change thing is conservation of energy. If we instead got a result that was in the same direction as the change, then we get this, then the magnetic field created by the induced current would create more induced current and more and more and more. And so any move would just result in a current that gets faster and faster and faster. And that's energy showing up out of nowhere, which doesn't happen. So the result that opposes the change that caused it is really a conservation of energy thing. We shouldn't expect these runaway infinite free energy results. We should expect limitations on how much energy the system has. Any other questions on that one? Okay, then let's try another example. Another one from that same praxis test. Did you want to try B or C on that one? Oh, 6A with the rotating wire. Let's try that one. So in this example, we have, or not a wire, or yeah, we have a magnetic field caused by a magnet. And we've got a loop of wire over here. And we're going to rotate this around this axis so that the point marked A, which was over here, is now above the plane of the page, which I think just means out of the page. So we're going to rotate it so that it now looks like something like that. Basically, we're taking this loop of wire and rotating it like this. So it's now shaped like that. So this edge is close to you and this edge is far from you. And we want to figure out what's going on in terms of flux. Is there any flux, or is there any changing flux? Is there induced current? So let's take a look at the magnetic field. This magnet is creating magnetic field with the usual dipole shape. So like coming out of one end, curling around back to the other end. But all we care about is this region of space. In this region, which direction is the magnetic field from this bar magnet?
The magnetic field will point like left, right? Because it's going from the north to south pole.
It should be coming out of the north end and eventually looping around back to the south end. But in this region, the magnetic field we care about is just to the left. Same thing here. So let's take a look at this from the perspective of flux. In this situation, is there magnetic flux?
No.
And how can we tell there's no flux there?
Because the surface normal is like into or out of the page, right?
Yeah, if we choose, whether we choose outwards or inwards, the surface normal is perpendicular to the magnetic field. So theta is 90 degrees, and therefore there is no flux. We can also look at this conceptually as we've got this loop of wire. The magnetic field is just skimming along the surface. It's not really going through the surface, it's just skimming along the surface. So there's no throughness there, which means no flux at all. What about in this situation? If we've rotated the loop of wire like this, do we now have flux?
Yeah, it's like the maximum flux.
Yeah, this is lots of flux, the most it can possibly be. Even though the point is on the left, we still choose, yeah, the magnetic field is going to the left here, but the normal vector has to be perpendicular to the surface. So if we've got this loop of wire, the only options for a normal vector are this way or this way. Yeah, this way. So that would be out of the board or into the board. When we rotate it though, our options are now to the left or to the right. Because the normal vector, normal literally just means perpendicular in this context. So the normal vector has to be perpendicular to the surface inside the loop. And again, I usually visualize this as just like taking this loop and dipping it in bubble soap. So there's this surface of bubble film on it. That's the surface that the normal vector is perpendicular to. And so we're definitely going from no flux to lots of flux. There's definitely a large increase in flux. Theta in this case, well, let's actually choose a normal vector. Before, we could choose outwards or inwards. Those both lead to 90 degrees. So that in either case, that's going to be no flux. So there isn't really a reason to choose one or the other if we just look at initial. But for final, our options are a normal vector to the left or to the right. Which one would make more sense there? A normal vector to the left or a normal vector to the right?
The left.
Yeah, I would choose a normal vector to the left, specifically to agree with the existing magnetic field. So if we choose normal vector to the left, the angle between that normal vector and the magnetic field vector is what angle?
0.
Yeah. And this is why we have lots of flux mathematically. A times B times cosine of 0 degrees. Cosine of 0 is 1, so we just get A times B.
Casey, I just have a quick question. So when they say to be consistent about the normal line, that's if you're just staying in the same, basically, dimension?
Even in this case, actually, we want to make sure we're using the same normal vector relative to the loop. It's just that the loop itself is rotating. Because we've got this loop, and we're rotating it like this. Because we're specifically told that this point ends up above, or I guess in this case, it would be outside of the plane of the page. So if we take this and rotate it, so it looks like this, but we want to end up with an outwards normal or a leftwards normal vector. If we rewind that, so we had this vector, this loop, we're rotating it like this. And we want to end up with a leftwards normal vector. If we rewind that, we had to have started with a normal vector in what direction?
Into the page.
Yeah, we have to start with an inwards normal vector so that when we rotate, we end up with the normal vector to the left.
Okay, that makes sense. Thank you, Casey.
So I would say we're starting with an inwards normal vector. You could start with an outwards normal vector, but if you did, then when you rotate, you're going to end up with a normal vector to the right. And a normal vector to the right in the end would still work. It's just that the fact that it's opposite to the magnetic field means the angle would be 180 degrees. You'd end up with negative AB as the flux. And a negative flux is certainly possible. It just is the mathematics still works out just fine. It's just much more difficult to visualize what's going on. So I would just always choose the normal vector that results in the flux being positive whenever possible. In that case, we've got flux increasing, right? Flux increases. And we want to establish a directionality with that. Flux, again, is technically a scalar, no direction, but we can treat it as a vector in the direction of the normal vector. So flux is, well, we start with no flux, but as soon as we start rotating, we get some flux in the direction of the normal vector. Weak flux, then stronger and stronger and stronger. So if we've got no flux and then a little bit of flux and then more and more, that's a change in the inwards direction. So if the flux is changing in the inwards direction, but the negative sign of Faraday's law says take the opposite of that, then the right-hand rule suggests current flowing this way. So that would be counterclockwise from the viewer's perspective. So this loop of wire, as soon as you start rotating it, gets some counterclockwise current. And as you rotate it, so you've got counterclockwise current. Is that visible? Different color. There we go. So you've got counterclockwise current. As you rotate, it's now going to be counterclockwise when viewed from the left. So original situation, as soon as you start rotating, you get counterclockwise current. Once you get to here, it's now counterclockwise when viewed from the left. So the point of view kind of shifts because we're rotating the loop, but we're going to get current throughout the entire rotating process. As soon as you stop rotating though, as soon as you stop changing the flux, there's immediately no more current at all. The current only exists while you were in the process of changing the flux. Any other questions on that?
Yeah. Oh. It's okay, go ahead.
Oh, sorry. So would the induced current be counterclockwise? I'm kind of confused on that part.
Yeah, the induced current, the current that starts is flowing this way.
Mm-hmm.
As we rotate, the current continues to circulate in the same direction as it was. It's just that we're changing the orientation of the loop.
Okay.
We've got this loop, we've got current flowing like this. As we rotate the loop, current is still flowing in that same way. It's just that that same way looks a little different because the loop itself has rotated.
Oh, okay. On the question, it said like A was on the right, like on the after part, A was on like this, like where it was like at the far point. If we knew that, like, oh, A was like on the right side, I think.
It says A is above the plane of the page. So, so my thumb is A, we rotate, and A is now out here.
Oh, okay. So like would like this like question, it depends on where you put like out or into the page kind of, or above the plane?
Well, the fact that current is flowing in the direction it does just has to do with the fact that we're rotating it like this.
Oh, okay. Yeah,
you get this current.
Yeah, I was kind of confused on like the A part, like because it's like the current must be directed downwards at point A, so I was a little confused at that part.
Yeah, current at point A is.
Okay, that's it. Okay.
Yeah. The notation being used here is horrible because it is difficult to draw in 3 dimensions.
Right.
But
okay.
what's happening is current circulating this way.
Okay, thank you.
And delta flux, the delta flux is positive in the sense that the flux is increasing. So we take a direction opposite to the normal vector. So normal vector, but the flux is increasing, so we take the opposite of that. We get current circulating this way. So it's still going to be counterclockwise.
I have a question. So how did you find like the direction again of the current? The direction of the current.
Using the negative sign in Faraday's law, that just tells us that the direction of current has to be opposite to the direction of change in flux. We know the flux is in the process of increasing, and we're treating the normal vector as inwards, so that's the direction we care about. an inwards normal vector that's increasing is becoming more and more and more inwards. So the changes in the inwards direction, Faraday's law negative sign says take the opposite of that. So point your thumb in the opposite direction, and the curl of your fingers tells you the direction current is flowing.
Okay, so it's because it wants to point like, I mean, relative to like the first picture, it wants to point outwards. And so that's why in order to, sorry, what is it after that? Like it wants to point outwards, so then it's going to do the opposite?
Well, the flux is changing in the inwards direction. So the opposite of that is outwards.
Oh, yeah, okay. And so then that's why the current would be.
Take the opposite, and your fingers tell you the direction of current circulation.
Okay, thank you.
Mm-hmm. All right, I've got to get to a meeting, but we can continue more examples in the review session tomorrow. Please email me if you have any specific examples you want to work on, and I will see you then.